Entropy change in an irreversible process. Consider the gas of problem 5.8. Calculate the final entropy of the gas in terms of its initial entropy before the piston was released. Show that the entropy change is positive. So delta S is positive and S in terms of S0 is what we're after. So I remember problem 5.8. You can see that there is a piston with mass m, cross-sectional area A. So this piston exerts a pressure P bar gas is equal to mg over A at equilibrium. So this piston was released, and we had a monatomic gas with new moles. We had a change of state from initial volume and temperature V0 T0 to final volume and temperature V final T final, and we calculated what these values are in problem 5.8. Now we're going to calculate the entropy change. Now this is an irreversible process, so we cannot use this process. So this is irreversible process. Now, the entropy is a state variable. Therefore, when we calculate the entropy change from initial to final, this is independent of the path taken. So basically, I can consider a reversible process. Therefore, consider the following reversible process. Reversible quasi-static process. So what I'm going to do is I will go from V0 T0 to first V final an intermediate temperature T intermediate using I'm going to do this using adiabatic compression. Then I'm going to follow this with V final T intermediate to V final T final using isovolumetric process. And these are all done quasi-statically, so I can easily calculate the entropy change. So I can call this state 0. I'm going to state A, and then I'm going from state A to state B, which is my final state. So the entropy change will be entropy change from 0 to A plus entropy change from A to B. The entropy change from 0 to A is integral from state 0 to state A d bar q over t, and this is going to be 0 because I'm doing adiabatic process, because d bar q is equal to 0. And when I calculate the entropy change from A to B, I have to do an integral from the intermediate temperature to final temperature d bar q over t. And since I have from A to B, V is constant, isovolumetric process, dE bar is equal to d bar q minus p bar dV, which is going to be 0. So instead of d bar q, I'm going to write nu cv dt, which is the change in the internal energy of the gas. So this will be the integral from T intermediate to T final nu cv dt over T, which is nu cv natural logarithm T final divided by T intermediate. So therefore, the entropy change I'm looking for from 0 to final state, or from 0 to B, is equal to nu CV natural logarithm T final divided by T intermediate. So now I have to calculate what T intermediate should be. So the first process that I'm doing is adiabatic compression. So let me start working on the adiabatic compression. In this process, I have pressure times P bar volume to gamma is a constant, or temperature times volume to gamma minus 1 is a constant. So that's a property of the quasi-static adiabatic process. And if I calculate gamma minus 1, since this is a monatomic ideal gas, gamma is 5 over 3, it is 5 over 3 minus 1, which is 2 over 3. So I have T0 V0 to the power 2 over 3 is equal to T intermediate V final to the power 2 over 3. Therefore, I can calculate T intermediate. T intermediate is T0 V0 divided by V final to the power 2 over 3. So therefore, I can write for the entropy change, delta S will be equal to nu CV natural logarithm T final divided by T intermediate, where T intermediate is T0 V0 divided by V final to the power 2 over 3. So I can write this entropy change from initial state to final state as nu CV natural logarithm T final divided by T0 V0 divided by V final to the power minus 2 over 3. Or I can write this as nu CV natural logarithm T final over T0 V final over V0 to the power 2 over 3. Okay, so let's calculate T final divided by T0. T final divided by T0 is, so first I have to check what T final was. T final is here, 3 over 5 T0 plus 2 over 5 mg V0 over nu RA. So I substitute here 3 over 5 T0 plus 2 over 5 mg V0 divided by nu RA divided by T0. This gives me 3 over 5 plus 2 over 5 mg V0 over nu R T0 A. And for V final divided by V0, I have V final from problem 5.8 here, 2 over 5 V0 plus 3 over 5 A nu R T0 over mg. So I substitute here 2 over 5 V0 plus 3 over 5 nu RA T0 divided by mg multiplied by 1 over V0. This will give me 2 over 5 plus 3 over 5 nu RA T0 divided by mg V0. Okay, so For the entropy change here, if you look at this product, T final minus T0 minus 3 over 5 multiplied with V final divided by V0 minus 2 over 5, you would have for minus 3 over 5, you would have 2 over 5 mg V0 divided by nu r T0a and multiplied with 3 over 5 nu r a T0 divided by mg V0, and you can see that these will cancel, and you have 6 over 25. So this product is 6 over 25. So I have T final over T0 multiplied by V final over V0 minus 2 over 5 T final over T0 minus 3 over 5 V final over V0 plus 6 over 25 is equal to 6 over 25. So these will cancel, and I will have in T final over T0 parentheses V final over V0 minus 2 over 5 is equal to 3 over 5 V final over V0. So therefore I can write T final over T0 is 3 over 5 V final over V0 divided by V final over V0 minus 2 over 5, which can be written as T final over T0 is equal to 3 over 2 V final over V0 divided by 5 over 2 V final over V0 minus 1. So I take the bottom into 2 over 5 parentheses. So 3 over 5 divided by 2 over 5 gives me 3 over 2. So this is basically T final over T0 written in terms of V final over V0. So if I go back to my entropy change, delta S, which is written here, nu CV ln T final T0, V final V0 to the power 2 over 3. This can be written as nu CV natural logarithm T final over T0. And I can write this as minus 2 over 3 nu CV natural logarithm V0 over V final. So I can write it this way. And this becomes, the entropy change becomes in 3 over 2 if I substitute for CV 3 over 2 R, so it's 3 over 2 R nu natural logarithm T final over T0, which is 3 over 2 V final over V0 divided by 5 over 2 V final over V0 minus 1 multiplied with V final over V0 to the power 2 over 3. Because it was a minus, I made it reverse the denominator and the numerator. Okay, so I obtained this expression for entropy change. So V final over V0 equals to 2 over 5 plus 3 over 5 A nu R T0 over mg V0. I define this as X. Then I find that the entropy change will be equal to 3 over 2 R nu natural logarithm 3 over 2x over 5 over 2x minus 1 x to the power 2 over 3. So then I find that the entropy change can be written as 3 over 2 r nu natural logarithm 3 over 2 x to the power 5 over 3 divided by 5 over 2 x minus 1, and this is basically s minus s0. So therefore I find that with x is equal to 2 over 5, so x was defined here with this definition of x, 2 over 5 plus 3 over 5 a nu rt0 over mgv0, I have the entropy change equals to this quantity. S minus S0 is given by this value. So I want to take a look at the value of x. I have a nu rt0 divided by mgv0. These are all positive quantities. So I note that x is a positive value because there is no negative volume. So for delta S to be positive, the entropy change to be positive, I need to calculate delta S is basically 3 over 2 r nu. Then I have natural logarithm 3 over 2 x to the power 5 over 3, and then I have minus 3 over 2 r nu natural logarithm 5 over 2 x minus 1 for the entropy change. So if 5 over 2 x minus 1 is positive, you would have 5 over 2x is greater or equal to 1, and x would be greater or equal to 0.4. And for the natural logarithm of a quantity to be positive, you would require y is greater or equal to 1. So therefore I have in this case 3 over 2x, so y is equal to 3 over 2x to the power 5 over 3 divided by 5 over 2x minus 1 should be greater or equal to 1, and therefore 3 over 2x to the power 5 over 3 should be greater or equal to 5 over 2x minus 1 for delta S to be greater or equal to 0. So it has to be, for it to be positive. So I look at the extremum points of y. So if you take a derivative with respect to x of 3 over 2x to the power 5 over 3 divided by 5 over 2x minus 1 and set it equal to 0, you will find the extremum points. So first derivative of the top gives me 3 over 2 times 5 over 3 x to the power 2 over 3 multiplied by the bottom minus the derivative of the bottom 5 over 2 multiplied by the top 3 over 2 x to the power 5 over 3, this divided by the bottom squared 5 over 2 x minus 1 squared must be equal to 0. So I find that 5 over 2 x to the power 2 over 3, 5 over 2x minus 1, minus 15 over 4, x to the power 5 over 3 must be equal to 0. In x to the power 2 over 3 parentheses, I have 25 over 4x minus 5 over 2 minus 15 over 4 x is equal to 0. So if I have x equals to 0, then I would have natural logarithm of 0. That is not possible. X equals to 0 implies, so let me look at the definition of x. X was defined here, so that means v final is equal to 0. So since v final is not 0, this is not possible. So I cannot take this as an answer. The second one is basically the parentheses. I have 25 over 4x minus 15 over 4x, 10 over 4x minus 5 over 2 is equal to 0, 10 over 4x equals to 5 over 2, and that means x is equal to 1. So if you set x is equal to 1, you will find that y is equal to 3 over 2 divided by 5 over 2 minus 1, 5 over 2 minus 1, which is 3 over 2, so y would be equal to 1. So that means since I have y should be greater or equal to 1, y equals to 1 is the minimum point. I can see that delta S must be greater or equal to 0, because delta S greater or equal to 0 implies y is greater or equal to 1, and that condition is satisfied. So really the entropy change is positive in this process. Okay, so let's go back. We're using the result of problem 5.8 to calculate the entropy change. The problem 5.8 process was irreversible. We had a piston that was released, and the final in the final configuration I had T final, V final. Initial configuration I have V0, T0, and in this case I calculated V final and T final as given in the problem solution. And now I'm calculating the entropy change. Because it's an irreversible process, I cannot use this process. I have to use a quasi-static process going from the initial to final state. So I chose to use adiabatic compression and then isovolumetric process. For the adiabatic process, the entropy change is 0 because the d bar q is 0. For the isovolumetric process, the d bar q is equal to dE bar, which is nu cv dt. So nu cv dt over t integral nu cv ln t final over t intermediate. I use the adiabatic compression. Tv to gamma minus 1 is a constant in order to calculate the temperature here. So I basically find that the intermediate temperature is T0 times V0 over V final to the power 2 over 3, and the entropy change is a nu Cv ln T final over T intermediate, so I substituted that here, and I find that I need to know the ratio T final over T0 and V0 over V final to the power minus 2 over 3 to calculate the entropy change. So I used the answers problem that I found in 5.8, substituted them here, and calculated this entropy change. And then I have defined the ratio V final over V0 as x, and the entropy change was written totally in terms of V final over V0, and that's basically S minus S0, so I calculated the entropy change. But for this entropy change to be positive, I have to check the function inside the natural logarithm. That has to be greater or equal to 1. So I looked at the extremum points of that function, and I find that there is one extremum point that is at y is equal to 1, x is equal to 1, and that is the minimum point. So delta S is greater or equal to 0 because the minimum value of y is 1. This was my requirement.